So thank you everyone. Today, we'll be talking about object-oriented programming and Rust, how they mix together and how they can work. First of all, why this talk? So the point is that I really literally grew up with object-oriented programming, and I actually liked it. And then I decided to unlearn it after a while. And this talk explains the journey, what happened, what I was doing. And this is the journey eventually I came to Rust. So things I worked on professionally. I worked on large embedded system, telecom witch stations, JIT compilers, Mono, V8 in Google, game engines inside Unity 3D, collaborative virtual reality on the web, distributed systems, blockchains, and distributed systems which are, let's say, eventually consistent. And now I'm working on operational research and logistics. So I did lots of things. I've seen lots of ways to design software. And along this journey, I started mostly with C++. You have to think late 80s, early 90s. Then Java, C#, and I was always thinking in terms of classes. And then I explored TypeScript, then Clojure, Haskell, OCaml, Go, Erlang. Now I work with Rust full time. And the point is that it took me decades to think differently. I was always thinking in terms of classes first, and now I think differently. And I want to explain what happened. And the point is why. Why did I decide, so to speak, to unlearn object-oriented programming? Is object-oriented programming bad? And the short answer is no, it's not. The principles are solid, and solid is an acronym which came from Robert Martin, Uncle Bob, and stays for single responsibility principle, open closed principle, least code substitution principle, interface segregation principle, and dependency inversion principle. I'm not going to describe them at length in this talk. This is not a talk about the principles of object-oriented programming. I'm just saying the principles are good. If you follow these principles, design your software, the software will be maintainable, it will work well, that's fine. So if the principles are okay, what's wrong? And to understand what's wrong, we should understand what object-oriented really means. There are principles, yes, but there are practices and there are technologies. And the problem is that we usually get these things backwards. So in theory, you should start from principles and define your practices and design your technologies so that those practices work well according to the principles. What we do is actually start from technologies, which are programming languages, development environments, tools, and in OOP, object relational mappers, dependency injection frameworks. We start with the tools, and how do we write code? We are not critical. We take technical features and we just use them, because for us, if a feature is there, it must be good. So the core issue is that in mainstream object-oriented languages and technologies, bad practices are actually encouraged by the tools. And those practices go actually against the good principles. And in my opinion, Rust is doing better. And so this is the gist of the talk. Let's start to think about problematic object-oriented practices. Often you end up with a jungle of dependencies, abstraction through inheritance, the abuse of virtual methods. Then there is the new operator, which is a strange construct that gets in the way. Often it is very easy to leak references to internal state of things, and there is pervasive mutability everywhere. So the problem is that typically when you look at the object-oriented code in the field, you see all of these things. And let's see why they are wrong. Thinking about dependencies, there is Joe Armstrong, which is the creator of the Erlang programming languages, that made this quote. It says, you wanted a banana, but what you got was a gorilla holding the banana and the entire jungle. This is about dependencies. So how does this happen? Let's start with a simple abstract example. We have a small class with three properties, like name, surname, whatever, three properties. software evolves, the class gets large, too large. You have to think about many properties and also many methods. Then you understand that for single responsibility principle, you have to split it. And then you break it up. But then the problem is that each helper class too often needs references to all the other parts. So person becomes something like this. You have 3 different aspects modeled by 3 different classes. But each helper class too often has a reference to the main class and a reference to others, because these aspects depend from each other. And the dilemma is that large classes are bad because they have implicit internal dependencies. When you have a very large class, each method of the class has full visibility of all the others. So it's very, very easy to have full internal dependencies that are too large. But small classes introduce more references to other classes, which cause more dependencies. And truly independent classes are very, very hard to design. And usually, you just, for simplicity, put those references there, and then your design goes bad. Now you see how a banana requires a gorilla, that then requires a jungle. And if you want to use the software for the banana, you get your entire jungle into your process. And how is Rust different in this sense? Well, the point is that in Rust, object references, especially references to mutable objects, are very, very hard to put somewhere. They are especially hard to store inside objects, because if you want to store a reference, you need to specify its lifetime, and this is infected in the code. So if you try to do it, you sort of refrain from doing that. And mutual references are exceptionally hard to use, like a person referring to an aspect of the person and the aspect referring back to the person coded in Rust is a small nightmare. And since dependencies are caused by references, the fact that the language makes the downsides of having references explicit, because if you introduce a references, you have all sorts of problems up front at compile time, then this encourages independent components. So this is sort of gently or not so gently pushing you into having less stateful dependencies around. Now, let's switch topic. Let's talk about inheritance and virtual methods. Inheritance mixes implementation inheritance with interface inheritance. This is typical in object-oriented programming. It's true that sometimes, like in Java, you can have interfaces and the interfaces inherit from interfaces. But the problem is that when a class inherits from another class, it's inheriting both the interface, the specification of the method it needs to have, and the state. And this is problematic. And virtual methods, in a sense, are even worse because they mix state definition with execution control flow. Like the nature of an object defines the control flow that will happen. And this is not always so good. Let's make a small example. Again, we have a person. And we must model the fact that youngers and elders choose gift differently. And in typical object-oriented style, we decide to model age classes with classes. And then we model age-related behavior with virtual methods. Then we have our abstract class, which is a person with a virtual method, we say abstract, which is choose gifts. And it gives us an array of gifts, whatever. And then we have a concrete class, which is youngster, which extends the person, where the method returns a Spotify subscription because a youngster wants to listen to music. And then we have the other concrete class, which is the elder, which instead wants a Financial Times subscription because he's serious, and that's fine. Now, this leads to apparently neat code because we can pick a person, and without needing to know the age, we can say, choose the gifts, and we have the gifts that have been chosen. But now tell me, what must happen if somebody, while the program is running, changes age? What needs to happen inside the program is that the object that we had is not good anymore. We cannot do anything with it to make it work again. We must destroy it and build another one. And this is really cumbersome. And the point is, we wanted clean code, but what we got was code that is hard to use when requirements change in a way we did not foresee. And this is due to the fact that the virtual methods embedded the dispatch into the state of the object, just the nature, not just values inside the object, but the actual creation of the object itself. How is Rust different in this sense? Well, the point is that, first of all, we need to take a step back. Who invented object-oriented programming? Well, Alan Key, the creator of Smalltalk, said, actually, I made up the term object-oriented, and I can tell you, I did not have C++ in mind. And we can say he also didn't have in mind Java or C# or all the object-oriented languages we normally use. So, given this quote, what did he have in mind? Well, point is, he was ahead of his time. Alan Key envisioned objects like cells. They were isolated, totally autonomous. There was no way to get into an object. This was totally impossible in the original object-oriented vision. And they could communicate only through message passing. Now, inheritance in Rust. Inheritance in Rust is only for pure interfaces. Traits can inherit from traits, but a type cannot inherit from other type, the implementation of the type. It can contain an instance of another type. So you can reuse definitions, but not inheriting from them, only containing them. While with traits, you have actual inheritance, but that's fine. And virtual dispatch in Rust, this kind of construct, when you create a dynamic trait and maybe you box it and you assign it to something, that involves dynamic dispatch. But the point is that the reference that you have is really totally opaque. It doesn't show up the inside of the object, because what you see is just the reference to the trait object. It does not expose the internal state. That it is impossible to mix a data structure definition with the virtual method definitions, because the data structure is the struct or the enum or whatever, and then you can implement the trait, but when you have got your dynamic trait, you don't see the structure anymore, unless you use dynamic any whatever, but it's cumbersome. It's not encouraged by the language. Which means that a boxed dynamic trait is really an object in the Smalltalk sense, because it's totally encapsulated. Now, a small rant and nitpick about the new operator. Every piece of state must be created in an object-oriented language invoking the appropriate constructor. And constructors are like magic functions different from other methods. And this has consequences, like transmitting states to other environments requires serialization when you create another kind of data object, which is not the original class. And recreating state requires deserialization, but picking the right constructor is always tricky. And changing class to a piece of data is, well, either cumbersome or totally impossible, which means that the dynamics of the code gets very, very rigid. And we see how Rust is different. Well, there is no new operator. Any function can return a new value, and there is no compiler magic in creating new values. New values are just created instantiating the literal and returning it. Dynamic traits are different because they have the vtable, but they are the special case. Normally, there is absolutely no problem with object creation. Then there is this other problem that we have in mainstream object-oriented code, which is references and mutability everywhere. I'm not going to make examples because everybody knows about this. In Java style, you model state with classes, and you store mutable state in objects, and you just take mutable state for granted. You are not even thinking about immutable state. The tool doesn't lend to modeling immutable state properly. Objects are just places holding mutable state. And this way of thinking made so that Rick Shickley, which is the creator of the closure programming language, defined object-oriented programming actually as place-oriented programming, which is sort of strange to understand. It sounds funny, but I say it was about time, because why does he insist so much about immutability? It's because of how time mixes with mutating values, and reasoning about values that change over time is very hard. And it's hard because you have to keep in mind all the possible consequences of the mutation. So Rick Shickley advocated for functional programming with pure immutable values because he was saying reasoning about mutation is too hard, just fix things. And the other basic assumption about mainstream object-oriented language is that everything happens on a global timeline. Everything is method calls, argument passing, object creations, assignments, and time and mutability mix very, very badly. How is Rust different in this sense? Well, Rust is imperative. It is possible to have mutable state in Rust. It is allowed. It's not the default. This is a key point. In Rust, to have something mutable, you have to add the mut keyword. But if you don't, you cannot change things. And the borrow checker steers you out of mutable state because it gets in the way. If something is mutable, you can do less things with it. So you are really steered away with that. And now, since we are talking about state, immutable values, let's talk about the contrast between object-oriented programming and functional programming. The idea is that in a functional approach to programming, you model state with plain data structures. You don't need to define classes. You just define the shape of values, preferably immutable, and you write every method not as a method, but just as a function, possibly pure, taking immutable values and producing immutable values with no side effects. And this functional approach, usually dependencies are stateless. You depend on functions, not on state. And control flow becomes explicit and easy to reason about. Deserialization becomes trivial, and testing is a breeze because dependencies are a breeze. And comparing the principles, object-oriented and functional programming, object-oriented principles make code understandable by encapsulating moving parts. So the point is that object-oriented code has complexity, but it shields you from complexity by encapsulating that. Why functional programming makes code understandable by minimizing moving parts, ideally not having them at all, because everything is immutable. It's constant. You just have pure evaluations everywhere. These are two totally different approaches to handling complexity. One is encapsulation, and the other is elimination of moving parts. And this is quoted from Working Effectively with Legacy Code. When you have a lot of complexity, you have to find ways to handle this complexity. And so I could say that a good practice is to do functional programming in the small and object-oriented programming in the large. Let's see what this means. In the small means if a computation should happen instantly, ideally instantly, it's not time-related. It's usually inside an isolated component with stateless dependencies. Then the suggestion is implement it in functional style using immutable values and pure functions. Sorry, glitch with slides. So this is something that you should do as long as it is practical. I say in the small because this usually happens in smaller components when you can really keep only stateless dependencies as pure functions. While in the large means if there are several possibly independent tasks that interact during time, and each task has its own state, and the event ordering can be chaotic. So these tasks are interacting with each other, but this really happens during time, and the semantics of time is important for the semantics of the execution of the whole system. Then I would say go for the actor model. Isolate each task in its own actor and make this actor exchange messages through channels. And by the way, async Rust totally shines at this. Because you can create independent actor at scale, you can have tens of thousands, hundreds of thousands of them in a process. It's not a problem at all. And you can really make them communicate using channels and have them evolve independently. So I would say that object orientation, taking inspirations from Erlang and Smalltalk, a lot of Erlang, you can say that each object is an actor with its own private state. They only interact through messages. And yes, events, messages can induce state changes inside objects or actor, but you can model these internal changes in a purely functional way. So inside an actor, you can model the actor as a pure function which takes the state, the incoming message, and produces another state and an outgoing message. And this is probably the best of both worlds. I would say that this slide about object orientation is saying what object orientation was meant to be in theory. Now, it was meant to be that in theory, but we can see that the mainstream languages don't encourage that kind of style. And I will do some historical considerations to explain why. Why did we get C++ instead of Smalltalk as a mainstream language? My theory, this is just my theory, in the 80s, computers were not so powerful. Proper object-oriented required totally decoupled objects, totally independent. You have to think of them as independent, isolated processes, and then you have to think about the computing power we had in the 80s. And we were just not ready to accept that. So we had an obsession with performance, and sometimes rightly so, because computers were very small, and C++ promised zero-cost abstractions. And in C++, a property access or a virtual method call is just a single machine instruction. And performance-wise, no dynamic system could compete with that. So we just decided, let's go for performance, optimize things, use C++, and we forgot about the actual meaning of object orientation. Now, how Rust is different? Well, programming is the art. Now, how Rust is different as a tool? We can say that programming is the art of finding the program that solves a problem among the space of all possible programs. This is quite strange to think about like this, but you can really say, I've got a programming language. There are all the possible programs I could write, and when some of them are the correct ones that solve the problem I had to solve. And programming, I am looking for this program among all the possible ones. Now, if we think about programming languages like this, I would say that in a low-level language, every program, correct or incorrect, is easy to write. The extreme, you write in assembly or machine code. It's very, very easy to write every sequence of code that is incorrect doesn't solve the problem. You don't have guidelines. There is nothing steering you towards the right program. While in mainstream object-oriented programming languages, it is correct programs, but badly designed, are easy to write. So the language is steering you towards correctness, but not necessarily towards a good design. While, for the reason we have seen in this talk, in Rust, correct and well-designed programs are easy to write. But because the way the language is built, if you try to write, let's say, a bad design, like with too many dependencies, too many references around, or too much mutable state that you try to expose, that is very hard to write in Rust. And I would say rightly so. Because at that point, when you write code, you are not just going to slip a reference inside a class because it makes your life simple for the piece of code you are writing now. Because yes, you can do it, and that single line of code will be easier to write. But the whole maintainability of the program will suffer. In Rust, you try to do it, you see it doesn't compile, you think, why? And you understand the consequences of that thing, and then you find a design where components are truly independent, because the language pushes you there. So the takeaway for the talk. I would say be critical with the programming language you use. If it has a feature, by default, don't use it, and use it only when you really see that it makes your code better. And you see that it does not cause problems. And learn lots of other languages besides the one you use. It will help you to think differently. You can learn Clojure, Erlang, Go, Swift, and Rust, Reason or Haskell. Clojure and Erlang in the simple functional style, Go, Swift, and Rust in the imperative style, Reason and Haskell in the purely functional one. Reason is OCaml with a better syntax. And then apply the lessons you learned, even if you will not change the language you are using. That's it. I've been a bit quick maybe, but the talk is done. I can take questions.